Okay, so in this talk, I want to speak about the use cases that we have in our task area in Nfdi4chem, revolving around the reuse of KBI and other ontologies, but mostly KBI, and the issues we have encountered with KBI regarding the modeling of chemical entities. The most important use case is, of course, our goal to let you find the right chemical datasets within the federation of the repositories that are harvested by the Nfdi4chem search service. As Bhavin mentioned yesterday, these are currently 5 repositories: Chemotion, NMArchive, Radar4Chem, MassBank, and Daros. And within the search service, we want to enable you to search for data sets or filter them by a particular compound, but also a group of compounds, as well as the observed, the used observation method or certain parameters of it. But today in this talk, I'm mostly interested in only talking about chemical compounds in this context, and more specifically, how we represent these by using ontologies to make our indexed metadata also available in an RDF knowledge graph, which should be one that is aligned with different standards like schema.org, DCAT AP on the more general level, and more specifically to PubChem RDF on the domain-specific level. Because our goal for early next year is to provide the metadata indexed in the search service also via a Sparkle endpoint that will allow you to do federated queries over available linked open chemistry data. But let's first have a look at the HTML representation of the metadata that we have. Within the search service, you can get a list of datasets associated with a specific chemical compound by searching for one of its structural descriptors, like its INCHI key, INCHI, or SMILES. But of course, this is only possible if the harvested repository provides at least one of these kinds of metadata within their metadata, so that the other ones can be computed with RDKit, as Barbin told you yesterday. Stuart said you're missing audio. Is everything fine with the audio?
Yeah, it's working.
Okay,
yeah, it's working.
Good. In the case of Chemotion repository, we have this metadata, and in Chemotion, it is possible to publish samples of chemical substances along with the data sets that were produced by various chemical analyses performed on these samples. Most often these analyses were done to be able to assign a chemical structure to these samples. And using the structure identifier or the chemical structure as an identifier allows Chemotion to link all these samples with the same assigned structure together, which in turn also allows to link together all the analytical data sets associated with the structure. So this way one can easily compare, for example, different 1H NMR spectra for the same compound done on different samples. And recording the links between the analysis and the samples that were performed on which the analysis were performed on makes it easier to find, for instance, outliers or other kinds of errors and biases that might exist due to a property of the sample and not one of the assigned compound structure. And having the samples also being available as reference compounds, reference substances via Chemotion would allow it to reproduce such results. Similarly, in NMArchive, structural descriptors are used as identifiers to find specific compounds, but more importantly, to find the data sets that are that contain the NMR spectra associated with these compounds. With regard to Radar4Chem and Darius, we have 2 more general purpose data repositories where researchers can deposit any kind of supplemental data to their publication. So consequently, their metadata schemas are currently not yet equipped to provide more chemistry-specific knowledge, such as structure descriptors for the associated compounds. And as Noura and I mentioned yesterday, we are currently working on overcoming this by using LinkML and possibly also LinkML map to provide a formalized representation of the subdiscipline-specific MICHI, the minimum information about chemical investigation standards developed by Nfdi4chem, to then have be interoperable with existing standards like DCAT, because we're with this approach trying to or working on extending the DCAT application profile into multiple subprofiles for each subdomain specific MICHI. And this work is currently in close collaboration with our colleagues from Nfdi4chem, as both of our consortia have very similar metadata requirements regarding chemistry or chemical entities. But since extending DCAT, the DCAT application profile for the provision of more domain-specific information is also relevant for other NFDI consortia, and as we heard yesterday, also for projects like PSDI, we are very much interested in collaborating with as many people as possible to have a commonly agreed upon approach for doing this. However, until we have these formalized MICHI and until these are taken up by such repositories such as Nfdi4chem and Darius, we still need to find ways to extract the chemical information we already have in more generic fields like the titles or uncontrolled keywords to enrich our metadata in the search service. And very often the chemical structures we find in such generic fields are rather referring to groupings of compounds instead of a specific compound. Which brings me to these examples of our finding the right dataset use case. Because sometimes searching only for a certain compound grouping or a substructure is all we need. Like, for instance, an organic chemist is interested in finding data sets about benzoic acid in general and not just about aspirin specifically. Or maybe a biologist wants to get data associated with natural occurring copper complexes with different oxidation states. And of course, it would be possible to perform a simple substructure query within the search service. However, when it comes to representing this metadata in RDF, or when one has to focus on very large compounds like natural products, where a substructure search might not be possible, it is important to have unique identifiers in form of an IRI of an ontology class that represents such a compound grouping. Yeah, and speaking of the representation of our indexed metadata in RDF, we can actually reuse most of the work done in the modeling of PubChem RDF. As you can see here, we can associate the compounds with their structural descriptors by instantiating the descriptor classes defined in ChemInf. The compounds themselves can be classified by instantiating either ChemInf classes that represent these compounds or those that represent a grouping of compounds with a similar structure. And we would want to get the latter rather by inference and not by manual curation, which is why we need KEBI or other auto-classification tools to be able to do this. But also we can classify a sample as a chemical substance, which should suffice in many cases, but we could also use subclasses like mixture if we need, for instance, to provide more information like its concentration. And what you can also see here on this slide, on the example of the ChemInf relation used in PubChem RDF between a registered chemical substance of the PubChem substance database and the normalized compound it is composed of, it is the fact that these two get conflated from an ontological perspective. We believe this is probably done out of necessity, as more fine-grained provenance data on the substances is often not available. Yet even if so, whereas in commotion it is available, wouldn't it be better to rather use a more general relation like the row composed primarily of to make this ontological distinction explicit? That's a question I would like to discuss later. But now coming back to the need for having compound grouping classes in KEBI, like I said, with the use cases, this would help us a lot to annotate data sets, not just for using auto-classification tools, but also to build good ontology-aware user interfaces when we do have the need to do some manual curation. But as you can see here, there are gaps in KEBI currently concerning some of these grouping classes. So we would be very interested in ways to close these gaps to address the use cases I talked about earlier. And what I'd also like to point out regarding some issues we encountered when working with KEBI and which are often brought to us by some confused chemists within Nfdi4chem is, for instance, the most prominent example, the way that atoms are modeled in KEBI. For one, we have the atom branch, which is supposed to represent the elements of the periodic table, including their isotopes, rather as abstract classes. And then, as you can see by the definition of the molecular entity class, we also find atoms and their corresponding ions being defined in various subclasses of the molecular entity branch. So telling the chemists which of these two branches they should use for data annotation is thus not often as clear as it should be, which can hinder building up their trust in ontology-driven workflows. And following rather old threads on various GitHub issues, it becomes apparent that in most cases, the atoms and their ions defined under the molecular entity branch of KEBI seem to be the ones that we need when it comes to describing our data sets. Another issue that often confuses our chemists is the labeling of the molecular entity class itself, although it actually refers to the molecular level. As you can see from its definition provided here, many chemists are irritated by the use of the word molecular. Clashing with the developments in chemical theory, they use it more commonly to refer only to molecules. The source of this confusion might be the fact that the definition of molecular entity was taken almost verbatim from the IUPAC Gold Book, in which the use of the word molecular might still cause some irritation, but it should not be considered as problematic. But in an ontology, however, we should rather opt for having turn labels and corresponding definitions that are as ambiguous as possible. So such issues need to be addressed, and they should be addressed in KEBI because, as you can see here, a lot of people and systems depend on KEBI. So we need KEBI as an ontology for chemical entities. And so many ontologies, we use it in order to represent chemical entities and assays as parts of materials or as participants in processes. And they also often use it in other ontologies to define classes because of the roles they play in various application, biological or chemical context. And I think it would be really great to get a better grip on the importance of KEBI as a dependency for other ontologies by having a more systematic and way more detailed analysis of its reuse than just the already impressive list of ontologies depicted here. The ontologies I have inspected more closely are, of course, those related to our use cases in Nfdi4chem, so the chemistry-related ones. And here you can see the named reaction ontology RxNO, which reuses KEBI, mostly KEBI compound grouping classes for its logical definition to define reactions and to specify the reactants, products, intermediates, solvents, or catalysts of reactions. Yet this axiomatization is not complete, and we hope that once we help to migrate RxNO to an MOP to ODK as well, that we can fix this together with the community. But in order to be able to do so, we depend on KEBI, of course, then to have all the grouping classes we would need for that. And looking into the molecular process ontology, MOP, we can see here that there's also a need for improving the axiomatization of basic reactions that MOP defines. But here we more often also have to deal only with atoms instead of compound grouping classes. So again, the question of whether to choose KEBI's atom branch or molecular entity branch pops up. The same is the case for CHMO. Here we would like, for example, to regroup the NMR spectroscopy branch to achieve a better usability. We would like to be able to group NMR spectroscopies not just by the probe nuclei, but also by other axes like dimensionality or pulse sequence. And for maintainability reasons, such a multi-inheritance hierarchy should best be done by axiomatization, which CHMO actually has already started and defined 7 of 40 plus NMR spectroscopies logically based on the probe nuclei. It did so by defining a probe's atom relation, and we're using mostly atoms from KEBI's atom branch. Yet, adding to the confusion, it did not import these atom subclasses along with their parent atom class, but instead subsumed them under the molecular entity branch, except for the lead-207 isotope, which already exists as isotope under the molecular entity branch. So even the CHMO developers seem to be confused by KEBI back then. And the comment on the probe's atom relation also highlights this, as only the atoms in KEBI's atom branch are logically connected to the KEBI nucleus class. So yeah, assuming that the wrong subsumption is not that much an issue of CHMO and maybe more of KEBI and being assured in this assumption by the way in which the molecular entity branch is used to define analyte assays in CHMO, as well as the statements made in the issues I referred to earlier. Wouldn't it be better to merge the atom branch into the hopefully then relabeled molecular entity branch to have atoms along with their ions and isotopes rather be defined there instead? Because as you can see here with these examples of trying to define logically NMR spectroscopies via the probe nucleus axis, doing so would make things way more or way less complicated and much easier. Yeah, and to summarize, but looking at the time, I will not summarize that much. We need KEBI, we depend on KEBI for the reasons that I told you. And yeah, thank you for your attention.
Thank you very much, Philip.